Hello everybody, welcome to section 4.2, and today we're talking about exponential functions and their applications. Now we're doing something slightly different, so I'll go through and we'll talk about the idea of a definition of an exponential function in the first place. And we'll talk about graphs of basic exponential functions along with some domain and range ideas along with their transformations, things to consider in that. We also talked something called about the natural base, e, and some applications of the exponential functions. So let's start. Let's talk about this idea. What is an exponential function in the first place? Well, here's our definition. If we say f of x equals b to the x, where b is greater than 0, b is not equal to 1, and x is in the set of real numbers. And all of that looks really nice, but the question is, well, what does all of this mean? One thing that we can say right now is that in the exponential function, the base b is fixed, and it's the exponent that's variable. Note, this is a little bit different than what we did the last time, where we had x as the base in our polynomials, and we had a fixed exponent for each of the terms. So, for example, right, if we want to think about how this is working, right, this is versus a polynomial term, right, and in a polynomial term, we had something like y is equal to something times x to the nth power, right, plus x to the n minus 1th power, where the exponent was fixed, right, and the base was variable. So how is that changing? Well, before we get too far into that, we should remember some of our rules for exponents. If you recall some of these things, we had one that talked about our multiplication of exponents, right? A to the m times a to the n is a to the m plus n exponent. We had a rule for subtraction that said a to the m minus n exponent. We had a rule that told us to multiply our exponents when we had this arrangement, a to the m raised to the nth power. We had a rule that told us anytime we raised a number to the 0th power, the result was equal to 1. And we had another rule that told us that as long as our base a was raised to a negative exponent, it was the same thing as 1 over a to the n, so it changed the position of that base. So what we need to do is we need to examine the behavior of some of this kind of expressions. So let's take a look at a specific kind of exponential function. Let's consider the function f of x equals 4 to the power x. What happens with this function? Well, we can automatically do a few things. Like, for example, if I were to tell you that x is equal to 0, how do we know what y is? Well, y is equal to 4 raised to the power 0, and we know that by rule that's equal to positive 1. So we have a graph that must pass through the point 0, 1. We would say that at x equals 1, y is equal to 4, because y is equal to 4 raised to the first power, and any number raised to the first power is itself. So this is the kind of graph that must pass through a point like 1, 4. This is also the kind of graph that if we said y is equal to 2, x is equal to 2, then y must equal 16. So at 2, we would go find 16 on our graph and plot it over here. If we kept on going, if we said y equals 4 to the 3rd power, we know we would get 64, and we could keep going in this direction. We are noticing one thing, however, is that the graph's value seems to be getting very large the higher we go. What happens with the negative numbers? Remember, x can be any real number here. Well, in this case, let's try it at x equals negative 1. Y equals 4 raised to the negative 1 power. Well, if we remember what that means, that's the same thing as 1 over 4 to the first power, which is just the same thing as 1/4, or 0.25. So pretty close to the x-axis down there. Then we said at negative 2, we try out x, and we're going to find y is equal to 4 raised to the negative 2 power. Well, 4 raised to the negative 2 power is the same thing as 1 over 4 to the second power. And so this one goes to 1/16. You'll note that it doesn't matter what negative number I put in the exponent position, I'm not getting a negative number out, just a very, very small positive value. So if I were to plot this function, what would happen? Well, I would get a shape that looks roughly like this. And we note that as x gets larger and larger, y gets larger and larger. On the other hand, as x gets smaller and smaller, y gets really, really close to 0, but never quite gets to x equals 0. And this is a characteristic of all exponential functions. And some of these properties are things that we can use. Now you'll note the other thing is that we don't have to limit ourselves to x values that are along our whole number values, right? We could also do something like 4 to the 1/2, right? If we think, well, 4 to the 1/2, what does that mean? If you recall, at x equals 0.5, we are in fact saying that y is equal to 4 raised to the 1/2 power. And if you recall, that is the square root of 4. So it's equal to 2. We can go to 3/2 and find out what happens right there. Well, we should pass through 8, right? We could go to 0.1 and find a value right here slightly above 1. Or if we went to 0.9, we might find a value slightly less than 4. But if we take all those values along this graph, we're going to get this increasing shape each and every single time for all of our exponential functions. So we need to look at some characteristics of this kind of function coming up in the next video.